Foreign is expanding. In 1929, we discovered that we are made of chemical elements forged in the centers of stars. A realization in 1957 that forever changed our understanding of our place in the universe. The sky isn't just pretty to look at, it's a window to the insanely powerful universe we live in. So much happens beyond our sight, and yet we on Earth often remain oblivious to the universe's true nature. Why are we here? Why do we have stars and galaxies? It could have been something else entirely. Even though these cosmic events could eventually impact us, we tend not to pay attention until things become serious and, well, it may be happening again. Throughout history, Betelgeuse has been one of the brightest stars in the sky, but recently it has begun violently vibrating and something potentially terrifying is unfolding. Join us as we dive into what's happening with Betelgeuse and how it might impact both its future and ours. Betelgeuse is no ordinary star, it never has been. It's one of the largest stars ever discovered, with a mass roughly 20 times that of our Sun, and it makes our Sun seem small by comparison. This star, located over 640 light-years from Earth, is a supergiant. Though it might appear as just another distant star, its cosmic scale is monumental. If we could travel at the speed of light, it would still take us over 640 years to reach Betelgeuse. Under normal circumstances, bridging that distance would take over 12 million years, a time frame far longer than the entire span of human civilization. This perspective emphasizes the sheer power of this one star, now observed to be violently vibrating. We often see stars as relatively calm objects simply existing in space, regardless of their size, but Betelgeuse proves this isn't the case. Scientists are puzzled by the unusual vibrations. Betelgeuse has always been known as a pulsating red supergiant, constantly changing. When it expands, it appears brighter. When it contracts, it seems dimmer. These fluctuations in luminosity unfold over tens to hundreds of days, with Betelgeuse showing a brightness range from plus 0.5 to 0 magnitude. The shifts in brightness occur in recurring cycles, with the shortest lasting around 185 days and the longest extending up to 2,335 days. The phenomenon, called V-band magnitude, hit a low point in February 2021 when it measured at plus 1.614, which, while bright, marked a departure from Betelgeuse's customary radiance. Betelgeuse's reddish hue is due to its cooler surface temperature of approximately 3,500 Kelvin, notably cooler than our Sun's 5,500 Kelvin. Despite being one of the larger known stars, this cooler temperature and lower energy output make it appear dimmer than the Sun. It has largely remained a relatively stable star despite its pulsations, so what could explain the recent upheaval? One theory is that Betelgeuse's helium shell is burning as the star moves through its life cycle, exhausting the hydrogen in its core and converting it into helium through nuclear fusion. This evolution is expected in red supergiants. As hydrogen fusion slows, the outer layers expand, marking the star's transition to the red giant phase. In this stage, helium accumulates around the hydrogen-depleted core, where intense heat and pressure trigger a secondary fusion process called helium shell burning. Helium nuclei fuse to form heavier elements like carbon and oxygen, releasing energy that counters the gravitational force compressing the outer layers. Helium shell burning, however, is less stable than core hydrogen fusion, leading to periodic buildups and releases of energy, which can cause the star's structure to become unstable. The resultant fluctuations in energy output cause Betelgeuse to expand and contract in pulsations, leading to variations in brightness. These pulsations are like a heartbeat, seen as changes in luminosity. To unravel the mysteries of such pulsating stars, astronomers use techniques like photometry and spectroscopy. Photometry monitors the star's light over time, providing insight into its dynamic behavior, while spectroscopy analyzes emitted light across wavelengths to reveal information about its temperature, composition, and motion. These methods allow astronomers to create a comprehensive narrative of the star's behavior. Additionally, computational models simulate Betelgeuse's internal dynamics, bridging the gap between theory and observation. They replicate processes like nuclear reactions and fluid dynamics, providing a clearer picture of the star's evolution. Within stars like Betelgeuse, convection, a process moving heat from the core to the surface, may also contribute to the observed pulsations. The convection currents act as a celestial conveyor belt, carrying energy to the surface and causing fluctuations in brightness. These currents cycle between increased and decreased energy transport, translating into pulsations. In binary star systems, material transfer may also influence pulsations. Here, two stars orbit a common center, and one may transfer material to the other, disrupting the recipient star's equilibrium and triggering pulsations. This material exchange affects the recipient's structure and behavior, leading to rhythmic fluctuations as the star seeks balance between gravity, radiation pressure, and internal nuclear reactions. Historically, stars were studied as isolated bodies, but material transfer in binaries has been occurring for ages, now observable thanks to advanced telescopes and research techniques. An unsettling possibility remains, however. The pulsations could indicate that Betelgeuse is nearing the end of its life cycle and may go supernova. Betelgeuse, like other massive stars, has balanced gravity and nuclear fusion for most of its life, but that balance won't last forever. Gravity, the inexorable force drawing massive objects together, could soon end this dance of equilibrium. The powerful gravitational force of Betelgeuse exerts a pull on the matter within it, trying to collapse the star inward due to its substantial mass. Counteracting gravity, nuclear fusion reactions occur in the star's core, converting lighter elements like hydrogen into heavier ones like helium. This fusion generates immense energy, creating an outward pressure that balances the inward pull of gravity, stabilizing Betelgeuse and preventing it from collapsing under its own weight. Over time, as Betelgeuse consumes its nuclear fuel, the balance shifts. The availability of hydrogen fuel decreases, reducing the core's energy output. As a result, outward pressure weakens, causing the core to contract under gravity. This contraction raises the temperature due to matter compression, and the increased temperature within the core triggers a new phase of nuclear fusion. Now, the core becomes hot enough to fuse heavier elements like helium and carbon, which creates even heavier elements and releases energy. This shift from hydrogen fusion signifies a new phase in the star's life, eventually leading to an iron core. Iron is unique as its fusion requires more energy than it releases, disrupting the energy balance maintained by previous fusion reactions. Unable to generate sufficient outward pressure, the iron core eventually collapses under gravity, resulting in a supernova explosion. This violent event expels the star's outer layers at extraordinary speeds, filling the sky with bursts of light and energy. The immense shockwave generated tears apart the star's structure, sending its material into space with tremendous force. This release of energy can rival an entire galaxy's brightness, momentarily outshining countless stars. Betelgeuse is about 600 light-years from Earth, so a supernova would light up the sky for days or weeks. However, if Betelgeuse were closer, the effects would shift from a spectacular light show to a catastrophe. A gamma-ray burst GRB from a nearby supernova could disrupt Earth's ozone layer by breaking apart ozone molecules, weakening its ability to block harmful UV radiation. Increased UV exposure would harm human health, increase cancer risks, and affect ecosystems, marine life, and agriculture. The intense radiation could also generate electromagnetic pulses (EMPs), potentially damaging electronic systems, disrupting communication, and causing widespread power outages. These EMPs would affect interconnected systems like financial networks, transportation, and emergency services, leading to a breakdown in essential services until the supernova effect subsided, possibly lasting years.
Trying to compress the star's outer layers.
Beyond these immediate
But the thing
impacts,
is, helium
a
shell
supernova's
burning
energy
isn't as
release could
stable as
disturb
hydrogen
atmospheric
fusion in the
dynamics,
core.
causing
It can lead
unusual
to
weather
periodic
patterns,
energy
temperature
buildups
changes,
and releases,
and possibly
which makes things
massive
go down an
storms.
unexpected path.
These alterations would affect
fluctuations in
ecosystems
energy
and agriculture,
output can result
potentially
in
leading to
instabilities
reduced food
within
security.
the star structure. The
Short-term
increased
disruptions
energy
in
production
ecosystems
causes
could
the
impact
outer
species
layers to
reliant on
expand,
stable climates,
while the subsequent
potentially
energy
altering migration
release
patterns and
causes them to
reproduction,
contract.
or even wiping
These
out some
expanding
species
and
if the
contracting
changes last long
motions
enough.
manifest as pulsations.
If
causing
Betelgeuse were close
Betelgeuse's
enough to create a
brightness
black
to
hole,
vary over
its
time.
gravitational
The
pull would
intense
produce
energy
tidal forces
generated
that could
during
disrupt
helium
nearby
shell
celestial
burning
bodies,
can lead to
possibly
strong
causing
stellar
collisions
winds,
or even ejecting
especially
planets
in
from
red
their orbits.
supergiants like Betelgeuse.
The collapse into
These
a black
winds can
hole would
carry
also
away
generate
a
an accretion
significant
disk,
amount of mass
emitting
from the
intense
star's
radiation
outer
across the
layers.
spectrum,
The mass
which could
loss
harm
due
nearby
to these
planets'
stellar
atmospheres
winds contribute
and disrupt
to the
technological
redistribution
systems
of
like
matter
satellites and spacecraft.
energy within the star.
A massive
further
black hole's
influencing
gravitational
evolution.
influence could alter
The outer
planetary
layers
orbits,
pulsate outward
destabilizing
during
the solar
expansion
system's
and
equilibrium
inward
and
during
potentially
contraction
leading to
like
catastrophic
rhythmic
changes
breaths.
in the celestial
This rhythmic
balance.
pulsation